ChatGPT changed everything. In just 2 months, it reached 100 million users. For comparison, it took TikTok 9 months and Instagram 2 years to reach that number. Today, over 92% of Fortune 500 companies have integrated AI tools into their workflows. But here's what's interesting. Most people who use these tools have no idea how they actually work. They type questions, get answers, and treat it like magic. That's fine if you're just a casual user, but if you're a developer, understanding the technology behind these tools isn't optional. It's the difference between being replaced by AI and being the person who builds with it. In this video, you'll learn exactly what large language models are, how they generate text, why they sometimes hallucinate, and what this means for your career as a developer. No PhD required, no complex math, just the practical concepts you need to build AI-powered applications. Let's break down what an LLM actually is. The acronym stands for Large Language Model. The L for large means these models have billions of parameters. GPT-3 has 175 billion parameters. GPT-4 is estimated at over 1 trillion. Claude 3 Opus has around 2 trillion. These numbers aren't just marketing. Size correlates directly with capability. The second L for language means these models are trained on text, massive amounts of it. Books, websites, Wikipedia articles, scientific papers, code repositories, Reddit discussions, essentially a huge chunk of the internet. The M for model refers to a mathematical function. In machine learning, a model takes an input and produces an output. For LLMs, the input is text and the output is also text. Here's the crucial insight that will change how you think about AI. LLMs don't actually understand anything. They don't think. They don't reason in the way humans do. They predict. Given a sequence of words, they predict the most probable next word. When ChatGPT writes a poem or explains a complex algorithm, it's doing one thing: predicting what text should come next based on patterns learned from training data. This is both less magical and more important. Let's dive into how LLMs actually generate text. It's called auto-regressive generation, and it works token by token. When you send a prompt to ChatGPT, here's what happens step by step. First, your text is converted into tokens. Tokens are chunks of text, roughly 4 characters each. The word development might become develop and meant as 2 separate tokens. Second, these tokens are converted into numbers called embeddings. Each token becomes a vector of hundreds or thousands of numbers that represent its meaning in a mathematical space. Third, these embeddings pass through the neural network. The transformer architecture, which we'll cover in detail, processes all tokens simultaneously and determines relationships between them. Fourth, the model outputs a probability distribution over all possible next tokens. It might say there's a 15% chance the next token is the, 12% chance it's a, 8% chance it's and so on. Fifth, one token is selected from this distribution. Usually, there's some randomness involved, which is why the same prompt can produce different outputs. Sixth, and this is key, the newly generated token is added to the input and the entire process repeats. The model generates text one token at a time, using everything it's produced so far as context. This continues until the model generates a stop token or hits a length limit. The entire response you see is built token by token, word by word. How do you teach a computer to predict language this well? Training happens in 3 distinct phases. Phase 1 is pre-training. This is where the model learns to understand language. It reads the internet, and I mean really reads it. Books, Wikipedia, news articles, GitHub repositories, scientific papers, forum discussions, trillions of tokens. During pre-training, the model plays a simple game. Given some text, predict the next word. It sees the cat sat on the and learns that mat is more likely than elephant. It sees a function definition and learns what code typically comes next. Do this trillions of times with billions of parameters, and the model develops an implicit understanding of grammar, facts, reasoning patterns, and even coding syntax. Phase 2 is fine-tuning. Raw pre-training creates a great text predictor, but not a helpful assistant. Fine-tuning teaches the model how to have conversations. Human trainers write thousands of example dialogues showing how a helpful assistant should respond to various prompts. Phase 3 is RLHF, reinforcement learning from human feedback. This is where the model learns human preferences. Human raters compare different responses and indicate which is better, which answer is more helpful, more accurate, safer, less harmful. The model learns to optimize for these preferences. This is why ChatGPT tries to be helpful and refuses certain requests. It learned that humans prefer helpful, safe responses. This entire training process takes months and costs hundreds of millions of dollars. That's why only a handful of companies can train frontier models from scratch. The transformer architecture is what made modern LLMs possible. Before it, we had a fundamental problem. Before 2017, neural networks processed text sequentially, word by word, left to right. This created a bottleneck. By the time the model reached the end of a long sentence, it had largely forgotten the beginning. Long-range connections were nearly impossible. Then came the paper "Attention is All You Need" from Google researchers. It introduced self-attention, and it changed everything. Here's how attention works. Consider the sentence. The cat sat on the mat because it was tired. When processing it, the model needs to know what it refers to. Is it the cat, the mat? With attention, every word can look at every other word simultaneously. The model learns that it should strongly attend to cat because cats get tired, mats don't. This attention happens mathematically through queries, keys, and values. But here's what made transformers revolutionary. Everything happens in parallel. Every word attends to every other word at the same time. This makes transformers extremely efficient on modern GPUs, which excel at parallel computation. Transformers also use multiple attention heads. Think of these as different perspectives. One head might focus on grammar, another on semantic meaning, another on long-range dependencies. The model combines these perspectives for richer understanding. Every major LLM uses the transformer architecture: GPT, Claude, Gemini, Llama, Mistral. The details differ, but the core insight remains: let every token attend to every other token. Let's talk about context windows. This is where many developers get confused, and understanding it will save you time and money. The context window is the maximum number of tokens an LLM can process at once. This includes both your input and the model's output. Think of it as the AI's working memory. Different models have different limits. GPT 3.5 started with 4,000 tokens, about 6 pages of text. GPT-4 offers 8,000 or 128,000 tokens depending on the version. Claude 3 pushes to 200,000 tokens. Gemini 1.5 claims 1,000,000 tokens. But here's what really matters. When the context fills up, information gets lost. The model doesn't gracefully summarize, it simply cannot see tokens outside the window. In a long conversation, earlier messages disappear. The AI might repeat itself or contradict what it said before. There's also a quality issue called lost in the middle. Models tend to pay more attention to the beginning and end of the context. Information in the middle gets less attention. A study from Stanford showed that models performed significantly worse at retrieving information from the middle of long context. For developers, this has huge implications. Long documents need to be chunked strategically. Chat applications need to manage conversation history. RAG systems need to place relevant information carefully. Here's a pro tip. Structure your prompts with critical information at the start and end. Summarize key points. Don't assume the model remembers everything just because it's technically within the context window. More isn't always better. Let's be honest about what LLMs can't do. Understanding limitations is just as important as understanding capabilities. First, hallucinations. LLMs generate plausible sounding but completely false information. They'll confidently cite papers that don't exist, make up statistics, or provide incorrect code that looks correct. This happens because the model predicts likely text, not true text. Second, no real-time information. Training data has a cutoff date. GPT-4's knowledge ended in April 2023. Claude's in early 2024. They don't know about yesterday's news or recent library updates unless you tell them. Third, reasoning failures. Despite impressive performance on many tasks, LLMs struggle with complex multi-step reasoning, especially in mathematics and logic. They can appear to reason while actually pattern matching from training data. Fourth, inconsistency. Ask the same question multiple times and you might get different answers. Temperature settings control randomness, but even at low temperature, outputs vary. This makes testing AI applications challenging. Fifth, no true memory. Each conversation starts fresh. The model doesn't remember your previous sessions unless you're using a system with persistent memory built on top. Sixth, cost at scale. API calls add up. A single complex prompt can cost cents. Multiply that by thousands of users and hundreds of interactions, and you're looking at significant expenses. Understanding these limitations helps you build robust applications. Always validate outputs, implement fallbacks. Don't use LLMs for tasks requiring factual accuracy without verification. Design for eventual consistency. Let's get practical. How should you actually use this knowledge as a developer? First, think in tokens, not words. API pricing is per token. Context limits are in tokens. A token is roughly 4 characters or 3/4 of a word. Code and non-English text use more tokens than English prose. Always check token counts before sending expensive prompts. Second, prompt engineering matters. Clear, specific instructions get better results. Include examples when possible. Break complex tasks into steps. Tell the model what format you want. These techniques work because you're providing patterns the model can follow. Third, choose the right model for the task. Don't use GPT-4 for simple classification when GPT 3.5 works fine at a fraction of the cost. Use larger contexts only when needed. Balance capability against cost and latency. Fourth, validate and verify. Never trust LLM output for critical decisions without verification. Implement guardrails. Use structured outputs when possible. Have humans review important results. Fifth, understand the ecosystem. OpenAI, Anthropic, Google, and open source models each have strengths. OpenAI has the largest ecosystem. Claude excels at long context and code. Open models give you control and lower cost at scale. Sixth, stay current. This field moves fast. New models release frequently. Capabilities improve. Prices drop. What's state of the art today might be obsolete in 6 months. Follow the developments. Let's wrap up what you learned today. LLMs are large language models that predict the next token based on patterns learned from massive datasets. They don't think or understand. They're incredibly sophisticated pattern matchers that have learned from trillions of words. The transformer architecture revolutionized this field by letting every token attend to every other token in parallel. This enabled the scale that makes modern AI possible. Tokens are the fundamental unit. Everything from pricing to context limits is measured in tokens. Understanding tokenization helps you optimize costs and build better prompts. Context windows limit what the model can see. Larger isn't always better due to cost, latency, and the lost in the middle problem. LLMs have real limitations: hallucinations, knowledge cutoffs, reasoning failures, and inconsistency. Build your applications with these in mind. As a developer, this knowledge helps you write better prompts, choose appropriate models, manage costs, and set realistic expectations. In the next video, we'll get hands-on. You'll learn how to actually call these models from your code using the OpenAI, Anthropic, and Google APIs. Will cover authentication, pricing, error handling, and best practices. If you found this helpful, subscribe for more AI and developer tutorials. See you in the next one.